Okay. So I am still stuck in grading limbo, grading pre-cal tests. I have to have those done by Friday. Um, but tomorrow is Halloween and my afternoon evening with my daughter, so I know I'm not gonna do it tomorrow. So I'll probably end up doing it over the weekend. But could be worse. Some classes are just barely taking. All right. So section 4.3 is on maxima and minima. So we're going to start talking about the interesting points, which are sometimes called critical points. So that's why this guy's condition is critical, because he's at a critical point on the graph. Yes, math humor is awful. I didn't post a video for the last problem. I just spaced by the time I finally got home. I did check through the web work and there isn't one like that. So we did talk about the structure. I'm gonna call that good enough. If we move at a good speed, we should be able to get through 4.3, like most of it today, finish it up on Friday, and then we should have time for questions. So make sure to dig into the related rate stuff, make sure they make sense or not. So you can have those questions maybe ready for Friday. All right, so absolute extrema, extreme points are highs and lows. So this parabola here, does it have a maximum or a minimum? Yes. Now, why do we call it a minimum? Yep, so the graph turns around there. And then when we say it's a minimum, it's not like the x value is a minimum, right? Like the x values just kind of plot along. So what is making it minimal there? Yeah, the y value. So that point has the lowest y value. So we would say this has an absolute minimum at x equals 1. Let me put it here. An absolute minimum of -4 at x equals 1. Like that's the kind of phrasing we use when we start labeling these points is the where it is the x coordinate, the what it is the y coordinate. And we got more of that on some of the further slides in here. It's more explicit. Like on this crazy slide. So these are the book definitions. You will not have to regurgitate these. We're just going to talk about them so we understand the very clinical way it's written. So f of x has an absolute maximum at x equals c if f of c is greater than or equal to f of x for all x. So as long as f of c, which is a y value, is the biggest y value the function ever touches, then it's an absolute maximum. And then likewise, a minimum is the lowest point for all of the x in the domain. So together, those are called absolute extrema, because that's the plural of extremum. So when we say the extremum is, that would be the y value. So what is that extreme value? It's the absolute highest value of like 10 or the absolute lowest value of -15, I guess. The extremum is at, this is our where or when it occurs. So it looks like at x equals -2.8 there, or x equals 5. So y values versus x values. And part of the reason we're going to the effort of being this explicit is because this is the easiest mistake to make on web work, is confusing which thing goes in which blank. Because it's like the extremum is or the extremum is at. It's really easy to miss the at there that changes what you want to type. So the is what the absolute high or low value is, which is the function value, so it's the y value. And then the where is it at is the x value that it occurs at. So looking at this very beautifully graphed thing, does this graph have an absolute extrema? All right, what does it have? So we can see it's got an absolute lowest point. The absolute minimum is -1 at x equals +1. So like our coordinates for this point are 1, -1. So the minimum value is -1, and it occurs at x equals 1. Now, what about our absolute max? So if it's infinity, then we say there isn't a definitive value. I think of it like infinity isn't an actual number, it's an idea. So I can't have it as an answer to what's the absolute max value. It'll tell you what to type, so it might be ND, yeah. But no. Single. No. So we have that idea of infinity because that's what's happening. It is infinitely going up. Or at least that's the assumption we make whenever a graph hits the edge of the box. That we assume there's an arrow there saying it keeps going forever and ever. If they wanted it to stop there, they actually have to zoom out a little and physically put points to say it stops. With stopping points? Yes. No, I'd just say no absolute max. So the infinity here is like, here we're saying there isn't one because the graph just grows and grows and grows. So I was saying no single value because it's like any x value I would say is the biggest. There's always another one that's bigger. So just be like absolute min here, absolute max, none. I haven't dug into WebWork to see how WebWork wants you to indicate that, but it should say in the directions on the problem. All right. Now, well, we got stopping points. So what does it appear the highest this graph goes? One more. Yeah. So it makes it all the way up to 12. And then what about our absolute low? Yeah. Now, as far as our location, the wheres, it looks like our absolute min occurs at x equals 2, and the max appears to occur at x equals 4. Absolute max is 12 at x equals 4. I'm tired of writing the word absolute. Absolute min is -4 at x equals 2. Like if we were talking about actual, like where the function inputs and outputs had like associated units, this would make a little more sense because then we might be saying like the absolute max is 12 chickens. So at 4 weeks, you'll have 12 chickens, and at 2 weeks, you'll have, all right, -4 doesn't make sense, but. And this is why mathematicians suck at coming up with application problems. I mean, chickens, really? All right, now we get another weird one. So hard to see exactly where the extrema occur, but it looks like somewhere in here. We're getting up to a value of 5. And then somewhere down here, looks like we're hitting a -5. But that X value is harder to say. So sometimes all they want is just the Y values. So absolute max for this graph is 5. Absolute min is -5. Okay. So I'll sometimes like kind of hold my hand horizontally when I'm looking at a graph and think like, what's the low? What's the high? To remind myself that it's a Y like level almost. But sometimes we get really silly looking graphs like this. Now the line segment in and of itself, not bad. But what makes this one weird? Yeah, that open circle. So looking, I got an absolute min. That's going to be -1. And it also happens to occur at x equals -1. Horrible mess. So because of the open circle, if I tried to pin it down and say, oh, obviously it's 4.999. Well, 4.9999 is higher than that and closer. So no matter how many nines I put, all of them, there's always another closer number to 5. 5 itself, though, is not actually reached by the graph. It gets closer and closer and closer, but it never actually hits 5. So this graph does not have an absolute maximum value. Now, if we were taking a limit, the limit would approach 5. So if we filled in the dot, then we'd have an absolute max at 5. But when we have these open circles, we just get closer and closer and closer, but we can't count it as a max or a min. All right, so just looking at this graph, we want to talk about, start moving towards this idea of what we call relative or local extrema. So we can have a point that's not the absolute highest for the whole graph, but if you zoom in just right close around it, it is the high point for its little close selection neighborhood of points. So like in here, just past that negative 2.5, that guy's a max for his, little collection of X values right around there. And then over here, around the negative 3.5, that's a relative low. But we also see our absolute max. And our absolute min. So now from a calculus perspective, what's the same about all those points? So what have we been talking about in calculus this whole time up till now? Derivative. What is derivative? What does it tell us? The slope of the tangent line. All right. So if I start thinking about the slope of the tangent line, or maybe if you will, like my roller coaster car on the track, where is it pointing? Like, how is the slope going when I get up to the top? What's happening? Yep. So every one of those, it's a turning point because the slope is turning from positive to negative or from negative to positive. And that was all backwards to y'all because I was doing it from my perspective. So uphill slope, downhill slope, flattens out slope. So the absolute max and min have a slope of 0. But there are those extra points, those relative maxes and mins. So let's see where the notes go. All right, so if I look, got a derivative of 0 here and here. So at x equals 0 and x equals 1. So that's a local max and a local min. But what is the absolute highest this graph gets? Where is its absolute highest point? So like x equals 0 is a relative max. It's the high point for its local crew. Is it the absolute highest point on this graph? No. So where do I go where I start getting points that are higher? No, just looking on the graph, because we don't know the y values here. So I can't tell you like even what this local max is, because I didn't get any tick marks. But just based on the appearance, I can see that when I get over here to the right, my graph starts getting higher. So my absolute max is occurring at x equals 2. So here, let me. Local max at x equals 0. Local min at x equals 1. The absolute max is at x equals 2. But what's going on with the derivative there? So remember, derivative is slope. So like at 0 here, I don't know what the max value is there, but I know the slope at that point is 0. And for x equals 1, I know the slope at that point is 0. At x equals 2, well, if I'm looking from the left side, looks like I'm getting a pretty steep positive. And then if I look from the right side, looks like I'm getting a pretty steep negative. So when we're getting two different values from two different directions, they're not agreeing. So if you ever have to ask yourself, like, well, which one do I choose? If there's any ambiguity, then it doesn't exist. The derivative does not exist there. The function still has a point there. It still has an absolute max it's hitting there. But if I was just using my calculus knowledge, taking the derivative, setting it equal to 0, I would miss that point because the derivative at that point is not 0. So it's, when I look at the graph, I'm kind of thinking like, I'm going up, I'm going up, I'm going up. Oop, I'm about to turn around and go down. So that it's kind of like when you get to the top of a roller coaster hill, right before you start going down, there's that like moment of weightlessness. Yeah. And then at the bottom, when your neck snaps back, that's when you're going from going downhill to going uphill. Mhm. So here they put the x and y axis. So that's our x equals 0, yes? And then looking at the graph here, I mean, it's a rough estimate. It could technically be like 0.001, but right around 0 is where I appear to be getting to a top of a hill and it turns back to go down. So the derivative there, I'm going from positive slope to now I'm getting like really laid back slopes. So these are where my slopes are like fraction values, like 1/2, 1/5, 1/10. And then eventually it flattens out. So a horizontal line has a slope of 0 because it doesn't have any rise or run. So if the slope there is 0, then the derivative there is 0. Mm-hmm. It's just doing it from the other way around. So we're getting down, but then they start flattening out. Sometimes I also think of it like a balance point. Like if I was going to take a tray and like balance it on top, the point that it would touch at and be balanced at, that's your max. That's where the slope is 0. All right, so our next slide. So local extrema are like absolute extremes, but they're only true around their little neighborhoods. They may or may not be the absolute. So local extremum occur when the derivative is one of two things. So the one we're going to see most of the time is that the derivative equals 0. Most of our graphs are like polynomials, so they're continuous everywhere. So we don't have those awkward sharp points that we were seeing in the previous picture. But some of the things we study, like the rational functions, those have spots where the function doesn't exist. But when we take the derivative may have some new spots that they don't exist that we still need to investigate for finding the absolute max or min. Yeah. Extremum is just the fancy word. So we're using the derivative to figure out where those points are. Like everything before, we were just looking at the graph. I have no clue what the equations are. But in calculus, we don't give you graphs. We're mean. We give you equations. So this is, for most people, like seeing the slope flattens out makes more sense when you see a graph, like you're seeing that balance point, that place where it tips over. So you can see the slope is 0. So now when I say f prime of c equals 0, like the hope is that it correlates to that picture. But what a lot of people get, especially if there's not as much emphasis on like what's happening in the picture, what does this mean to the graph? They just like, you take the derivative, you set it equal to 0, those are your extreme points. And that will actually take care of probably like 90% of functions. But we're going to have these kind of special cases every once in a while where the derivative doesn't exist, but the function may exist at that point. So these are what we call critical points. So critical points, wherever the derivative is 0 or wherever the derivative doesn't exist, which graphically doesn't exist typically means corner points or an asymptote. All right. So looking at this craziness, let's mark some critical values. So where is my slope 0? Like it's kind of weird, but it's flattening out there around -5. And then over here, it looks like I've got a slope of 0. Those are my only two 0 slope points. Now, I also don't want to pick up on any funky corner points. So we got a corner point there and a corner point there. So all of the critical points, we've got x equals -1, -2, roughly -3.5, and -5. Now, picking out those numbers it's a guess. Like doing it off a graph is very inaccurate. But looking at the graph, like I can see, okay, those are like relative lows and highs. Yeah, that makes sense. But what is my absolute highest Y value on this graph? So looking at the whole graph. So yeah, this one goes a little bit higher. It's like 2 point something. But are there points that are even higher than that? Yep, over here, it gets all the way up to 3. So we've got an absolute max of 3, but that's not any of the critical points. And likewise, if we look for the absolute min, that's way down here at, I guess, negative 0.6. So, like, we can identify critical points, but when we're looking at a bounded function, the other place we have to check for the absolute extrema is the endpoints as well. So it's like I just took you on a really weird tour through every way you could screw up these questions. With the hope being by seeing the mistakes, hopefully you remember it when you're working these problems yourself. So whenever we're looking for an absolute extremum, we look for all of our critical points where the derivative is 0, where the derivative is not defined or does not exist. And then also we look at the endpoints if we have definitive bounds on the function. So now we have a strategy. So if we're going to find absolute maximum or minimum without graphing, we first list our endpoints as possible suspects. Then we look for our critical values. So we take the derivative, set it equal to 0, look for points where the derivative doesn't exist. And then those are some of our critical values, our suspects on our list. These are all X values though. I don't know what the associated Y value is. And here I'm doing this from the equation, so I don't have the graph. Now, granted, we have Desmos, we have graphing calculators. We could go look at the graph. But like, especially when you're doing this on web work, the follow-up question is always, well, what is that absolute max value? What is the min value? So those are the Y values. So all of our suspect X values, we take each one, go back to the original function, plug it in, crunch the numbers, and we look at the Y values, and then it's literally just, who's the biggest? You're the max. Who's the smallest? You're the min. But like, notice here, Chris put original function in bold. So if you plug in the number and get 0, make sure you plugged it into the original function. Every rare once in a while, you will actually get a 0 as the Y value, but most of the time when you get that 0, it's because you went back to the derivative instead of the original function. All right, so remember the notes are in Canvas, so you don't have to like write all of these down. He also did have another little note here. Make sure the critical values that you're picking, your suspects, are within the endpoints. So sometimes when you do the derivative, you'll get a value that's actually further than where they told you to restrict. I don't know if we'll necessarily get that on this one. But we have the very ridiculous function x to the 4th times e to the negative x. And it's being defined on the interval from -2 to 9. And they want absolute max and min. All right, so our values to test. And you can write this as like a f of x table. You could just list the numbers like whatever you want to do. But we've got -2 and +9. That's our start of our list. Now we're going to do some calculus to see if we can get some more suspects for the list. All right, so x to the 4th times e to the -x. So as it is right now, it's a product rule. I could move the e to the x to the bottom, but then I'd have a quotient rule, and well, product rule is better than quotient rule. So that's a A times B situation. So I'm going to do my A prime, power down 4x, 4 minus 1 is 3, times, keep B the same, e to the -x, plus. Now I keep my A, which is x to the 4th, times, now I'm doing the derivative of e to the -x. Now we know our e is like our best friend because it's the laziest derivative. So it's going to be e to the -x times, our chain rule says we got to come up here and take the derivative of the power. So what's the derivative of -x? So that's x to the 1st. So we bring the 1 down times that negative sign. So it's a -1 times x to the 1 minus 1 is 0. So whenever we have a linear term, the derivative of that is just whatever the coefficient is. So this guy here is just going to be -1. But that's our, I knew it, called the stupid office. I knew they were going to call back during class. All right, so we have our derivative. Where? It's not x to the -1, it's just -x. If it was x to the -1, then yeah, it'd be -1x to the -2. But it's especially easy to do that when you're looking at it as a power, but now you have to think about it as not a power. All right, so I'm just gonna clean this up a little. So both of those have e to the -x. And since we're about to set this equal to 0, I'm gonna factor that out. And then I have 4x cubed, and it'll be minus x to the 4th. So finding our critical values, we're setting it equal to 0. We're asking when is the derivative 0? So now I have 0 equals this e to the -x times 4x cubed minus x to the 4th. That's two things being multiplied that are equal to 0. So either e to the -x is 0, or 4x cubed minus x to the 4th is 0, or neither are 0 and then there are no critical values. It is possible to get, all we do is check the endpoints. Make a little more room. All right, so e to the -x. If you're not thinking too hard, but hard enough, how do we cancel out e? We natural log. So if I natural log both sides here, The natural log of e to the something is just the something. So we have negative x equals the natural log of 0. Now, if you crunch natural log of 0 on your calculator, what does it say? It does say undefined or some sort of creative, I don't know what to do. It's because you asked it to do something impossible. So e to the negative x is just numbers that are getting increasingly smaller, but they're all still positive numbers. So this never happens. So there's no x values coming from that. So it's totally fine at e to the negative x equals 0. Never happens. Okay, ignore that. So now over here, 4x cubed minus x to the 4th. Well, those got some stuff in common. So I'm going to factor out that x to the 3rd. And that leaves me with 4 minus x equals 0. So now I got two things to solve. X cubed equals 0, which is just going to give me x equals 0. Very normal for that to pop up. And then we have 4 minus x equals 0, so x equals 4. So those are my two critical values that I'm going to add to the list. And then when I put them on that list, I want to kind of take a moment and just, all right, 0 is between -2 and 9. That one's fine. 4 is between -2 and 9. Okay, I can use both of those. But if we'd gotten like x equals 10, we'd chuck out the 10 because we're not looking at that section of the graph. All right, so I have 4 values here. One of those 4 is the absolute max. One of those 4 is the absolute min. Now we can actually get ties, in which case they're just both whatever thing. But to figure out what they are, we've got to go back to our original function, which is x to the 4th times e to the negative x. And this is where I bemoan not having a calculator that's not just my phone. All right, so open parentheses, -2, close parentheses, to the 4th power, close parentheses, times e to the -2. So that just ends up being e to the +2. So this gives us 118.224. All right, now our 9. 9 to the 4th power, good lord, times e to the -9. And that e is pretty powerful because this went from 6,000 something to 0.80969, blah, blah, blah. All right, now I plug in 0. 0 to the 4th is 0. E to the 0 is 1, so it's still 0. And now we're going to plug in 4. 4 to the 4th, which is 256, times e to the -4th. All right. 4.688. So what is our absolute max? Which point's the highest? X equals -2 gives us a highest value of 118.224. Now what about our absolute min? Yep. So our lowest value is 0 and it occurs at x equals 0. Now, real quick, I'm just going to graph it on Desmos so we can actually see the doodle. X to the fourth, e to the negative x. No, just right here. So I didn't get it all the way back to -2, but you can see the 0, and then it maxes around the 4 for the relative max. And then over here, it looks like it's just going to keep getting closer and closer to 0, but never get there. But back here at 0, it does actually touch 0. So even though it's got a horizontal asymptote, this one still has an absolute min. All right. So we will look at a product rule with a natural log next time. Go ahead and hit the stop recording.